All right, people, so let's do some examples of Stokes' theorem. This is a great theorem in this class now. So let's have our surface S be this hemisphere in three-dimensional space. It is given by the half of the sphere of radius 2 that would be centered at the origin, but we'll just look at the half where the y coordinates are bigger than or equal to 0. And we'll say, suppose that S is oriented in the positive y direction, which just means that we are given now a choice of normal vector field to S that points in the positive y direction. So here is a picture of that. So here is our surface S, and we are not capping it off here, so this back part is open. So there's this hole in it there. And the normal vector field n will point in this direction. So I've only drawn one of those vectors, but there should be one at every point. Okay, and let's see. So notice that the boundary curve here is a circle of radius 2 centered at the origin and sitting entirely in the xz plane, right? So the y coordinates are all 0 for that points along that boundary circle there. Okay. All right, so we might like to, trade a surface integral over this whole surface for just a line integral over this circle boundary curve, because we know how to parameterize circle boundary curves. That's not so bad. So let's say we're given this kind of strange looking vector field here, that big F of x, y, z is arctangent of y in the first component. It's e to the y plus 2z in the second component. And it's minus x in the third component. Okay, I don't know what I think about that vector field, but we'll take it for now. And let's also check that the curl of f, you can do this in your own home, that the curl of f is given by minus 2 in the first component, 1 in the second component, and minus 1 over 1 plus y squared in the last component. That is negative the derivative of arctangent of y with respect to y, I see. Okay, so we're going to first use Stokes' theorem, the sort of first way that we want to use it, where we'll trade the surface integral for a line integral. So we'll have this vector field here, curl of f. We will try to do the surface integral of this guy by instead trading it for the line integral of the original vector field along just the boundary curve C. So we'll need to parameterize C to be consistent with this chosen orientation here. And so if we follow the right-hand rule, say take your right hand and point your fingers so that they curl in the direction of the curve C, so that they point in the direction of the curve C, but curl inwards to the direction of where the surface actually is, then your thumb needs to point in the same direction as N when you do that. And so you can see here, if you try to go either way with your fingers on your right hand, that it's really this way is the way that you need to go to have your thumb pointing in the positive y direction. Okay. And so now I'd like to get a little bit of a better handle on that, because that looks like that might actually be clockwise in the xz plane. So if I write, here's the positive x-axis and here's the positive z-axis. So what I'm going to do is draw another picture off to the side here of the xz plane and look at how that curve is being traced out. And it looks like it's going this way, right? Now, that is not the way that we normally will parameterize a circle, so we're going to have to make a choice to sort of go backwards. So there's two kind of nice choices here. You could take the parameterization that we normally use, which would be like 2 cosine t in the first component and 2 sine t in the second or in the last component, and just negate one of them. And so you could just negate the first one, and that will turn the direction around for you. Or you could just interchange those two coordinates at right off and have no minus signs to worry about. So one of the differences here is that, okay, if for t varying between 0 and 2 pi, this curve, where will it start? I think this one will start at minus 2 comma 0, and that's back here, and move this way. And this curve if you start at t equals 0, it will start at the point 0, comma 2, which is up here. But that's fine. It doesn't matter really where you start. The point is that you want to just move in the right direction, okay? And both of these choices move in the correct direction at hand. So I'm going to go ahead and pick the second of these two choices. Okay. And so with that being said then, our vector field big F of x, y, z was given by arctangent of y in the first component, e to the y plus 2z in the second component, and minus x in the third component. So if we evaluate that along this parameterization r of t, we get, well, arctangent of 0 is 0, which is nice. E to the 0 is 1, so we get 1 plus, well, 2z. Z was 2 cosine t. So in the second component, we get 1 plus 4 cosine of t. And in the last component, negative x becomes, well, negative 2 sine of t. Okay, now this doesn't look like it's so bad to deal with, right? We also have that the tangent vectors to that parameterized curve, little r, are little r prime of t equals to 2 cosine of t in the first component, 0 in the second component, and negative 2 sine t in the last component. And so then taking the dot product of big F of r of t with little r prime of t, we get that 0 plus 0 plus 4 sine squared t. Ah, very nice. And so it follows then that the line integral along C of the vector field f is just the ordinary integral from 0 to 2 pi of this function 4 sine squared t with respect to t. So all we need now is the half angle formula for sine. So we will replace 4 sine squared t with 2 times the quantity 1 minus cosine of 2t. This guy then integrates to 2t minus sine of 2t, I think. Yes. And we'll evaluate this at 0 and 2 pi. And what do we get? Well, at 2 pi, we get 4 pi, and everywhere else, we get 0. Okay? So we'll end with that this line integral is 4 pi. And so for that vector field curl of f, this one here, maybe we'll call that g for a second. Stokes' theorem then says that the surface integral over that whole hemisphere of g equals to the same as this line integral that we did, which I'd like to say was a little bit easier to handle. And that turns out to just be the nice number 4 pi. All right. So stick around for the next video. I think we'll do another example along the same surface in space, but this time our example will work the other way, and we'll do a surface integral instead of doing a line integral. So we'll see you then.